Hello, student. So this is the ninth question of your tutorial 3. Okay, tutorial 3 that covers the content of learning outcome 3. Okay, so this is the ninth question. Okay, actually I put this kind of questions to give you idea how we can use our signal and system knowledge. Okay, how we can use our signal and system knowledge to analyze a real-time component. Okay, so these are some practical components we can we can come across our day-to-day engineering life. Okay, so this is a mixture. Okay, so there are many kind of mixtures. Okay, RF mixtures and signal mixtures. Okay, so they are using in communication systems. Okay, this kind of mixture. Okay, in microwave communication, RF communication, in many application we are using this kind of mixture. Okay, so I think this kind of question will help you to give you idea how we can use our basic signal and system knowledge to analyze or to study this kind of component. Okay. Okay. So we will move on to our questions. Okay. So we have a mixture here. Okay. Normally RF mixture has 3 ports. Okay. Normally RF mixture has 3 ports. Okay. So actually some mixtures are passive mixtures. Okay. There are some passive mixtures and also we can see some active mixtures are also there. Okay. So we have many kind of mixtures actually. Okay. In our lab also we have some mixtures. Okay. So once you visit to the lab, you can see this component. Okay. Okay. So normally it has 3 port. Okay. It is a 3-port device. Okay. It is a 3-port device. Okay. So one is input. Okay. One is input. Okay. Normally we input RF signal. Okay. RF range signal. RF range signal. Okay. And there is another input. Okay. Another input that is we are given normally low frequency signal. Okay, low frequency signal. So maybe it is generated by a oscillator or something. Okay, and in the output we can get an intermediate signal. Okay, intermediate frequency signal. Okay, so the frequency will be changed. Okay, so there are many applications. Okay, actually for many applications we are using this kind of mixtures. Okay. Okay, so we will see this. Okay, so here we have one input xt and there is another input from a local oscillator, that is yt. Okay, so it is said that the output will be the product of the input and local oscillator generated signal. Okay, so the output will be the product of these 2 signals. Okay, so these 2 signals are the input. Okay, so the output will be, let's say that output is zt. Okay, so output will be the first signal and a product of the first signal and this local oscillator signal yt. Okay. Okay, so this is the output of the mixture. Okay, in this given example. Okay, so this is the output of the mixture. Okay, and it is said that the xt will be sinusoidal signal. Okay, so that is sine 10t. Okay, and yt is another sinusoidal signal, and it is given as cos 2t. Okay, so you can see that this signal is a high frequency signal and this signal is a low frequency signal. Okay, and the output will be the product of these two signal, no? Product of these two signal, that is sine 10t into cos 2t. Okay, so this will be the output signal. Okay, so this will be the output signal. Okay, and we are asked to find the complex exponential Fourier series representation of the signal. Okay, so actually we know that when we have this kind of cos and sine terms, okay, it is easy to use Euler formulas and try to represent this as a Fourier series representation. Okay, so here also you can see that we have sinusoidal component, sine component. Okay, so here for this one also it is easy to use Euler formula. Okay, and we can directly get the Fourier series representation. Okay, okay, actually here you have a product. Okay, here you have product. I think no issue. Okay, because you already know that how this can be represent using the exponential terms, using the Euler formula. Okay, so it will be like this. So it will be e j 10t minus e minus j 10t. Both should be divided by half j. Okay, and it is multiplied by cos 2t. The cos 2t is e j 2t divided by 2 plus e minus j 2t divided by 2. Okay, so you can multiply these terms. Okay, so you can first multiply this one, then you can multiply this one. Okay, and this one. Likewise, you can write some components, some terms. Okay, exponential terms, and this will be your Fourier series representation. Okay, so this approach you can so you can get this approach. Okay, but here we are asked to, okay, so here we are asked to use this identity. Okay, here we are asked to use this identity. Okay, so can you see that why we what is the importance of this identity? Okay, actually we have so using this identity we can convert this product. Okay, so here we have a product, sinusoidal terms product, and we can convert it as it into a sum. No, okay, this product we can convert into a sum using this identity. Okay, actually that is the only help of this identity. Okay, so you can write this expression as a sum. Okay, sum of two sinusoidal signals, so that you will get a composite signal. Okay, so let's see how we can do this. Okay, so here you can see that it is 2 sine alpha cos beta is equal to sine alpha plus beta sine alpha minus beta. So you can divide this side by 2. Okay, and also you have to divide this side also by 2. Okay, okay, so here you have half sine alpha plus theta and half sine alpha minus theta. Okay, so so now this is cancelled. This 2 will be cancelled out. Okay, so you have sine alpha cos beta, then you have some sine terms. Okay, so you can directly use them. Okay, so Z is equal to, so you can see that sine alpha cos beta. Okay, so this 10t will be alpha, the 2t will be beta. No, sine alpha sine beta. Okay, so you have half sine alpha plus theta, alpha plus beta, that means 10t plus 2t, that is 12t, plus half sine alpha minus beta, alpha 10t minus 2t, so it will be 8t. Okay, so this will be your composite signal. Okay, so now we have found the Fourier series representation of many this kind of signal. So you can use that knowledge and you can uh, find the Fourier series representation easily. Okay. So I think before that you need to verify the period of this signal. Okay. That is the first thing you have to do, first step. Okay. So you can see that let's say this one is the signal 1 and this will be omega 1. Okay, and let's say that this will be omega 2. Okay, this 8 will be omega 2. Okay, so omega 1 is equal to 12. Okay, so you know that period t is equal to 2 pi by omega. Okay, so you have t, let's say that p1, okay, is equal to 2 pi by 2. That means 5 by 6. Okay, and in the same manner for a second signal omega 2, okay, it is 8, omega 2 is 8. Okay, so you know that T2 is equal to 2 pi by omega naught. Okay, omega 2 in this case, here it is omega 1, and in this case it is omega 2, and T2 you will have 2 pi by 8. Okay, so you have 5 by 4. Okay, so if you get T1 by T2, okay, T1 by T2, you have 5 by 6, 5 by 4. Okay, okay, so it will be 4 by 6. Okay, 5 by 6, 5 by 4. So 5 cancel out, and this 6 will be there, and this 4 will be going up. Okay, so it will be 4 by 6. Okay, so you have 2 by 3. Okay, so this is a rational number. This is a rational number, and so it is periodic. Okay, so it is periodic, and the period is, okay, period is 3t1 equal t2 to t2 is equal 5 by 2. Okay, so 5 by 2, it will be 5 by 2. Okay, 3t1. So this is, if you multiply this by 3, so you will have 5 by 2. Okay, or 2t2. If you multiply this by 2, you will get again 5 by 2. Okay, so you will get the 5 by 2. That is your the composite signal period. Let's say it is T naught. Okay, so T naught is equal to 5 by 2. Okay, so you know that omega naught is equal to 2 pi by T naught. Okay, so you have 2 pi by 5 by 2. Okay, so this 5 cancel out, this 4 you will get go up, so you will here you will get 4. Okay, so this is the omega naught of the composite signal, that is 4. Okay, so this result is very important. Okay, so that is 4, omega naught is 4. Okay, so let's write these terms, okay, as complex exponential terms. Okay, so I will write it again here. We said t is equal to half sine 12t plus half sine 8t. Okay, so this will be your signal, no? 12t plus 8t. Okay, okay, so using Euler formula, you already know the Euler formula. Okay, So using the Euler formula, you can write this as, okay, so Euler formula, you know that Ej theta is equal to cos theta plus j sin theta. E minus j theta is equal to cos theta minus j sin theta. Okay, so if I subtract this one from this one, this cos theta terms will cancel out. Okay, and I will get 2j sin theta. Okay, 2j sin theta, and this e j theta minus e minus j theta. Okay, to find the sin theta, I have to divide these two by 2j. Okay, so this is the sin theta. Okay, so you can express sin theta in terms of complex exponential terms. Okay, so I can use that result here easily. Okay, so I said t will be half, okay, 1 by 2j e to the power j. Here theta is 20 minus half 2j e to the power minus j 20. Okay, and in the same manner, I can write this term also, half 1 by 2j e to the power j 80. Okay, minus half 2j e to the power minus j 80. Okay, so I can write like this. Okay, so Z t will be, okay, Z t will be, so you can see that here you have 4j, 1 by 4j e to the power j. Okay, so so you can see that here we have verified that omega naught is 4. Okay, so I will use this with omega naught. Okay, so I have 4. So here 12, so I have to multiply by 3 t minus 1 by 4j e to the power minus j again. So here minus sign. Okay, so I will remove that minus sign from there. Okay, so here it is 4 minus 3t plus 1 by 4j e to the power e to the power j 4 2t minus 4j e to the power j 4 minus 2t. Okay, so these are the terms. Okay, so you know that this is omega naught, and this is omega naught, and this is omega naught, and this is omega naught. Okay, so this will be your k value. So here k is equal to 3, here k is equal to minus 3, here k is equal to 2, and here k is equal to minus 2. Okay, okay, so these are the k value. Okay, so I can write down the coefficients. Okay, so I have here k is equal to 3. That means I have C3. Okay, so that will be minus 1 by 4j. And here it is minus 3. Okay, that means C minus 3 I have. That will be, so this will be the coefficients. That is minus 1 4j. Okay, and so here the k is 2. That means I have C2 here. Okay. Okay, so this will be the coefficients. So it will be 1 by 4j. And here the k is minus 2. That means I have C minus 2. Okay, and the coefficients is minus 1 by 4j. Okay, so we have found the coefficients also. Okay, actually if you have right up to this level, you can get the full mark. Okay, you can get the full mark. No need to write these terms. Okay, for this question. Okay, for this question, you no need to write those coefficients also. Okay. Okay. So here, how many frequency components are there in the output signal? Okay. So you can see that if you have look at this one, okay, so this will be your output terms. Okay, so you have this frequency component and you have this frequency component. Okay, so these two are the frequency component we have. Okay, so we have two frequency component. Okay, so for this so this one you have two frequency component. Okay, two frequency component. And what are the harmonics? Okay, so we are asking the harmonics. Okay, so we have here, you can see that we have 3 and -3. So this will be, actually these two will be the third harmonics. Okay, this will be the third harmonics. Okay, and this is 2 and this is 2. Okay, so this will be second harmonic. Okay, okay, so we have only third and second harmonics. Okay, so here we have two frequency component and we have second and third harmonics. Okay, so that is the answer for this question. Okay, so here we are asked to draw the magnitude plot for the Fourier series coefficients. Okay, so we have already drawn the magnitude plot also. Okay, so we will see. Okay, so you can see that, so these are the coefficients. Okay, so these are the coefficients, Fourier series coefficients. Okay, and you can see that these coefficients are normally complex numbers. Okay, these coefficients are complex numbers. Okay, that means we can write this Fourier coefficients as x plus iy. Okay, in this form we can write. Okay, or we can use the polar form, that is this way. Okay, so so you can see that, so this is a complex value. Okay, so this ck is a complex value. So you know that for a complex number we have a magnitude. Okay, we have a magnitude. So this one is the magnitude, actually r. Okay, if it is in polar form. Okay, or if it is in Cartesian form, the magnitude will be x square y square. Okay, so this will be the magnitude of this ck. Okay, and also you can find the phase of the ck. Okay, if this is a complex number, there is a phase. Okay, so that phase is tan inverse y by x. Okay, so if you can't remember this stuff, you can please refer the complex number complex number notes. Okay, which you have learned in your mathematics subject. Okay, so for a complex number, this will be the magnitude, then this will be the phase. Okay, so you can see that. Okay, so you can see that so different k, for different k value, you will have different magnitude, and different k value, you will have different phase also. Okay, so if you plot, okay, if you plot those magnitude with respect to k. Okay, so ck magnitude, if you draw ck magnitude with respect to k, so you will have this kind of value. Okay, so magnitude will be a real value anyway. Okay, and you can see that if this complex number is, sometimes this imaginary part can be 0. Okay, so if it is 0, you will have a total real number x. Okay, so the x magnitude of x will be x. Okay, so so anyway you can find the magnitude like this. Okay, so if you plot it for different k. Okay, so this is k is equal to 0, 1, 2, 3, 4. So it is -1, -2, -3, -4, so on. Okay, so if you plot the magnitude of ck with respect to k, it will be the magnitude plot. Okay, magnitude plot. Okay, it will be the magnitude plot. Okay, it will be the magnitude plot. Okay, and if you so in the same manner, okay, if you plot the phase with respect to phase of this coefficients, phase of this ck with respect to k. Okay, so here k is 0, -1, -2, 1, 2, 3, so on up to infinity value. Okay, so if you plot that phase, okay, so there may be different phase, plus and minus phase. Okay, so that will be your phase plot. Okay, so this will be the phase plot. Okay, so here we are asked to draw the magnitude plot, only the magnitude plot. Okay, so very easy. Okay, so we have coefficients. Okay, so we have coefficients and we have k value only 3, -3, 2, -2. Okay, so if I draw the phase magnitude plot, okay, so I have to draw the magnitude, that is ck magnitude with respect to k. Okay, so here k value I have 3, -3. Okay, 2 -2, 2 -2, and 3 -3. Okay, so these coefficients only I have. Okay, c-2, c-2, c+2, c-3, c+3. Okay, so uh, these are the these are the component I have. Okay, these are the component I just have. Okay, uh, so I have to find the magnitude of this value. Okay, so you can see that in this case, these all are the pure imaginary parts. Okay, so you have to get the this is the magnitude actually. Without considering the plus or minus value, this will be the magnitude. Okay, 1/4. Okay, so here you will have 1/4, 1/4, and here you will have 1/4. Here also you will have 1/4, and here also you will have 1/4. Okay, so this is the base plot. Okay, so that is the answer for this question. So please go through this kind of questions. Okay, you have in tutorial 3. Okay, so this kind of question will come to your exam and exam. Okay, so you should be able to answer this kind of questions. Okay, so if you have any problem, you can ask me again, then I will help you. Okay, thank you.